Introduction to Orbital Mechanics and Spacecraft Attitudes for Thermal Engineers. Part 4, Advanced Orbit Concepts. Before we conclude our discussion of orbital mechanics, let's consider briefly some advanced concepts such as transfer orbits, orbit plane changes, aerobraking orbits, gravity assists, the three-body problem, halo orbits, and the orbits for the Artemis and Gateway spacecraft. A transfer orbit is used to move a spacecraft from one orbit to another, such as raising the orbit of a spacecraft after launch or to set a spacecraft on interplanetary trajectory. The orbit is changed by changing the energy of the orbit. For this brief discussion, we'll focus on the case of determining a minimum energy transfer from one orbit to another. This minimum energy trajectory is referred to as a Hohmann transfer. Consider the case where we desire to set a spacecraft on an interplanetary trajectory from planet 1 to planet 2. Both planets are in circular orbits about the Sun. In these orbits, planets 1 and 2 are traveling at velocities v1 and v2 respectively. For a successful transfer, we need to ensure that the extent of our new orbit reaches from one planet to another. We see from the diagram that the half-ellipse has a semi-major axis a sub t, which is equal to the sum of the distances from each planet to the Sun divided by 2. Recall that the total specific energy of an orbit is constant and is given by the expression at the top. And we recall from our earlier study of the two-body problem that the specific angular momentum is also constant. Since the specific angular momentum is constant, we can evaluate it at any convenient location in the orbit. Here we'll consider para-axis, denoted by the subscript p. From our earlier work, we recall a couple of other expressions that we need as well. So if we begin with the expression for the specific mechanical energy and make the proper substitutions, we can show that the specific mechanical energy can also be expressed as a function of only the semi-major axis, as shown in the expression at the bottom. If we equate our two expressions for specific mechanical energy, and if we rearrange the equation, we can establish an equation for the velocity v as a function of radius r from the central body. With this expression, we can readily determine the velocity of planet 1, namely v1, and the velocity the spacecraft will need to be on a transfer trajectory, namely v sub t. The difference between these velocities, or delta v, is how much additional velocity is required to place the spacecraft on the transfer orbit trajectory. And since the spacecraft will be transferring from planet 1 to planet 2 over 1/2 of an elliptical orbit, the time it takes to transfer from one orbit to the other, denoted by t sub t, is 1/2 of the entire elliptical orbit period, as shown at the bottom. Next, let's consider the orbit plane change. A plane change is used to change the inclination of a spacecraft's orbit. Consider the spacecraft in the green orbit in the diagram to the right. We desire an orbit plane change to the red orbit. Here, we assume both orbits are circular. The difference in inclination angle is denoted by the angle theta, and since both orbits are circular and remain at the same altitude, we can say the magnitude of their velocities is the same and denoted by the letter v. We can construct a vector diagram representing the velocities of the green and red orbits. The change in velocity, delta v, is the orange vector shown. From trigonometry, we see that the magnitude of delta v is just twice the magnitude of the velocity times the sine of the half angle between the two orbits. A spacecraft would require a delta v of this magnitude executed in the proper direction to change from the green to the red orbit. Aerobraking is a technique to slow down a spacecraft in orbit about a planet with an atmosphere. Using aerobraking reduces the amount of fuel required to change in orbit. As an example, consider the Mars Global Surveyor spacecraft. Mars Global Surveyor made repeated passes through Mars' atmosphere so that drag acting on the solar panels and other surfaces slowed down the spacecraft. As you can see from the diagram at the right, drag force applied at the para-axis resulted in apoapsis change. Gravity assists are used to redirect spacecraft from one trajectory to another, but gravity assists also add energy to the spacecraft by stealing a small amount from the planet's orbit. Gravity assist has been used successfully many times. Here, the gravity assist strategy used for the Juno spacecraft is shown. Some missions use multiple gravity assists to achieve their objective. Much of the focus of this lesson has been on the two-body problem, but there are interesting consequences that arise when three bodies are involved. Two celestial body masses, which we'll refer to here as M1 and M2, and a third body where the mass of the third body is much less than the other two, such that it can be neglected. The two celestial masses can be a planet and a moon and its moon, or a planet and the Sun, the condition being that the two celestial bodies must orbit the same center of mass. In such a system, there are regions in space around the two primary bodies that can serve as gravitational nodes where spacecraft or other celestial bodies can collect. These are called Lagrange points. There are 5 such points. L1 through L3 are referred to as the collinear points as they lie along the line that passes through the two primary bodies. These points are unstable. Lines connecting L4 and L5 with the primary bodies form an equilateral triangle. These points are stable. From a historical perspective, the mathematics developed by Lagrange that showed the stability of the L4 and L5 Lagrange points led him to believe that asteroids might be trapped near these points. When the Sun and Jupiter are considered as the primary bodies, observations by Max Wolf in 1906 confirmed the existence of the first of many Jupiter asteroids at a Lagrange point. These clusters of asteroids are referred to as Jupiter's Trojans. Lagrange points are also useful for spacecraft orbits. As an example, the James Webb Space Telescope is to be placed at the Sun-Earth L2 Lagrange point. The Discover spacecraft is located at the Sun-Earth L1 Lagrange point. From this vantage point, it has a continuous view of the sunlit portion of Earth. A halo orbit can be established about the Earth-Moon L2 Lagrange point and is a prime location for a communication satellite link between the lunar far side and Earth. A spacecraft orbiting this point in space will always be in view of both the lunar far side and Earth, as shown in the figure. Not all orbits are described by the 2-body or 3-body solutions we've explored in this lesson. To give you an appreciation of the sophistication of the ability to design orbits and to plan missions, the proposed orbit for the Artemis 1 mission is shown here and involves a launch from Earth and a partial Earth orbit, after which it breaks free from Earth using a translunar injection burn, goes between the Earth and the Moon, and enters lunar orbit. From there, it enters a distant retrograde orbit where it ultimately departs and returns to Earth. The proposed Gateway will orbit in what is called a near rectilinear halo orbit, where on closest approach will get within about 1,500 kilometers of the Moon's surface and will be about 70,000 kilometers away at its farthest. This gives Gateway the advantage of being easily accessible from Earth orbit and serves as a staging point for excursions to the lunar surface and into deep space. In Part 4, we took a brief look at some advanced orbital mechanics concepts such as transfer orbits, orbit plane changes, aerobraking, gravity assist, 3-body orbits, halo orbits, as well as orbits for upcoming missions such as Artemis and Gateway. These examples give viewers a good appreciation of the applications of orbital mechanics. In the 5th and final part of this lesson, we'll discuss spacecraft attitudes and, in conjunction with the orbital mechanics we've learned, we'll show how these concepts can be used by thermal engineers to understand the on-orbit thermal environment.